How black holes bend space and time is often described in simple terms, as if these objects are powerful vacuums pulling everything nearby into a dark center. Many explanations focus on gravity as a kind of force that reaches outward, dragging matter and light inward once they come too close. In this familiar view, space is treated as an empty stage, time as a steady clock, and the black hole as something acting within that setting. This way of thinking feels intuitive, and it matches how gravity seems to behave in everyday life, where objects fall toward Earth and clocks appear to tick at the same rate everywhere. Yet even within this common understanding, there are quiet points of uncertainty. Gravity, when measured precisely, does not always behave as a simple pull, especially when mass becomes extremely concentrated. Astronomers noticed long ago that the motion of stars near dense objects did not fit neatly into the older picture of forces acting across empty space. Light itself, which was once thought to be unaffected by gravity, was observed to change direction when passing near massive bodies. These observations suggested that something more gradual and structural was happening, something that could not be fully captured by imagining gravity as an invisible hand pulling inward. The science that describes black holes is more nuanced than the idea of overwhelming attraction. It does not begin with sudden collapse or dramatic capture, but with slow changes in how space and time behave as mass increases. Rather than treating space as fixed and time as universal, modern physics describes them as flexible and connected, responding continuously to the presence of energy and matter. In this video, we will explore that response calmly, layer by layer, allowing each idea to settle before moving on to the next, without urgency or emphasis. Welcome to AstraFlow. Here, science drifts quietly, and understanding comes without effort. If you find this space helpful, you're gently invited to leave a comment or subscribe. Now, let's begin. To start, it helps to rest with the idea that black holes do not introduce a new kind of physics so much as they reveal the extremes of familiar laws. The same principles that guide the motion of planets and the ticking of clocks are present near a black hole, but they operate under conditions far removed from daily experience. When mass becomes very large and very compact, the effects on space and time become noticeable rather than negligible. What we call bending is not a dramatic event, but a smooth reshaping, one that grows stronger as mass becomes more concentrated. In everyday surroundings, this reshaping is so subtle that it goes unnoticed. Earth bends space and time slightly, but the effect is small enough that our senses cannot detect it directly. Clocks at different heights tick at measurably different rates, yet the difference is tiny. Paths through space curve gently, guiding falling objects along predictable trajectories. These are quiet expressions of the same process that becomes more pronounced near a black hole. Nothing fundamentally new appears. The scale simply changes. Black holes form when a large amount of mass is confined within a relatively small region. This confinement does not happen all at once. It is the result of long stellar lives, gradual fuel exhaustion, and the steady dominance of gravity over internal pressure. As a massive star runs out of energy, it can no longer support its own weight. The material begins to compress inward, increasing density. With each increase in density, the surrounding structure of space and time responds more strongly. As this response grows, the geometry of space becomes increasingly curved. Objects moving nearby follow paths determined by that curvature, not because they are being pulled by a force in the usual sense, but because the shortest paths available to them now bend inward. Time, too, responds. Process is slow relative to distant observers, not abruptly but progressively, as the gravitational influence deepens. These changes occur well before anything reaches what is later called the event horizon. It is important to notice the absence of sharp boundaries in this description. There is no sudden moment when space snaps or time breaks. Instead, there is a continuous adjustment, governed by well-tested equations. Even the most extreme regions near a black hole are connected smoothly to the surrounding universe. This continuity is a key feature of the scientific picture, and it allows astronomers to model black holes without invoking special exceptions or hidden mechanisms. Light provides one of the clearest windows into this behaviour. When light passes near a massive object, its path curves slightly, following the shape of space. Near ordinary stars, this curvature is small. Near a black hole, it becomes pronounced. Light can orbit, loop, or be delayed, not because it slows in the usual sense, but because the geometry it travels through has changed. Observations of these effects confirm that space itself participates in the motion we see. Time behaves with similar subtlety. A clock closer to a massive object ticks more slowly relative to one farther away. This slowing is not a malfunction of the clock, nor a local experience of delay. For the clock itself, time feels normal. The difference appears only when clocks at different positions are compared. Near a black hole, this difference grows gradually, becoming extreme only very close to the central region. Again, there is no sudden threshold, only a steady progression. The popular image of a black hole as a cosmic drain can obscure this gentler reality. Nothing is actively pulling from a distance. Instead, space and time have been shaped into a form that guides motion inward. Objects can orbit a black hole stably, just as planets orbit stars, provided they remain far enough away. Even near regions of strong curvature, motion remains lawful and predictable, following the same principles that govern the rest of the universe. As we settle into this understanding, it becomes clear that black holes are not isolated anomalies. They are part of a continuous spectrum of gravitational systems, differing in degree rather than in kind. The bending of space and time is always present, everywhere, though usually too subtle to notice. Black holes simply make this bending visible on a scale that can be measured and studied. This perspective allows us to approach black holes without fear or exaggeration. They are not interruptions in the cosmic order, but expressions of it under extreme conditions. By observing how space and time respond near them, scientists gain insight into the structure of reality itself, insight that applies broadly, not just at the edges of collapse. For now, it is enough to rest with the idea that bending is gradual, continuous, and deeply connected to mass and energy. There is no need to picture dramatic swallowing or sudden destruction. Instead, imagine a smooth landscape of space and time, shaped gently but firmly by what it contains. This landscape extends from the familiar to the extreme, without breaks or sharp transitions. In the next section, we will step back slightly, grounding this picture in the more familiar experience of gravity as it appears in everyday physics, before slowly moving again toward the conditions that give rise to black holes. For now, allow this initial layer to settle, like a slow adjustment of focus, bringing the structure beneath appearances quietly into view. Before black holes enter the picture at all, gravity is usually understood through ordinary motion and familiar experience. We see objects fall toward the ground, planets trace steady paths around the sun, and tides rise and fall in a slow rhythm. In this setting, gravity appears as a force acting between masses, something that reaches across space and influences how objects move. This description works extremely well for most purposes, and it formed the foundation of physics for centuries. It allows us to calculate trajectories, predict eclipses, and understand the broad structure of the solar system with remarkable accuracy. In this classical view, space itself remains fixed and unchanging. It serves as a backdrop, a three-dimensional stage on which motion unfolds. Time, likewise, is treated as uniform, flowing at the same rate everywhere, regardless of locational motion. When gravity is introduced, it does not alter space or time directly. It simply adds a force that changes how objects accelerate. For everyday conditions, this separation feels natural. Space seems empty and passive, and time feels steady and universal. As measurements became more precise, however, small inconsistencies began to appear. Certain planetary motions showed subtle deviations that could not be fully explained by simple gravitational forces alone. These discrepancies were minor but persistent. They hinted that gravity might not be acting through space in quite the way it was imagined. Instead of being an external influence applied to otherwise neutral space, gravity seemed to be connected more deeply to the structure in which motion occurred. One of the first clues came from careful observations of how light behaves. In classical physics, light has no mass and should not respond to gravity at all. Yet observations during solar eclipses showed that starlight passing near the sun was deflected slightly from its expected path. The amount of deflection matched predictions that assumed space itself was curved near massive objects. This result could not be accounted for by treating gravity as a force alone, acting in an unchanging space. At the same time, experiments with timekeeping began to reveal tiny variations in how clocks tick. Clocks placed at different heights above Earth's surface, or moving at different speeds, were found to drift relative to one another in predictable ways. These differences were extremely small, but they were real and measurable. They suggested that time itself was responding to gravity, not remaining separate from it. Once again, the idea of a universal unaffected time began to soften. To accommodate these observations, physics gradually shifted its description. Gravity was no longer treated as something acting within space and time, but as something that shapes them. Mass and energy influence the geometry of space and the flow of time, and objects move according to that geometry. In this framework, what we experience as gravitational attraction is the natural motion of objects following the curved structure around them. In ordinary environments, this curvature is gentle. Earth's mass bends space and time only slightly, so the effects remain subtle. A thrown ball follows a curved path not because space is dramatically warped, but because even a small curvature can guide motion over time. Similarly, clocks at different heights tick at slightly different rates, though the difference is far too small to notice without precise instruments. These effects are always present, quietly shaping motion and measurement. This perspective allows gravity to be understood as a continuous property of space and time, rather than a separate force imposed from outside. There is no sharp boundary between no gravity and strong gravity. Instead, there is a smooth range of curvature increasing with mass and density. The same principles apply everywhere, from the surface of Earth to the orbits of planets, to the environments near much more massive objects. Black holes emerge naturally within this continuum. They represent situations where mass has become so concentrated that the curvature of space and time becomes extreme. Nothing about the underlying rules changes. The equations remain the same. Only the values involved become larger. By understanding gravity in its gentler forms first, it becomes easier to approach these extremes without invoking special cases or dramatic exceptions. It is also important to note that this description does not remove predictability. On the contrary, it enhances it. By treating gravity as geometry, physicists can calculate orbits, light paths, and time differences with great precision. Even near very massive objects, motion follows well-defined patterns. Stability and order persist, even as curvature increases. As we hold this foundation in mind, black holes can be seen not as isolated phenomena, but as part of a broader, consistent picture of gravity. They sit at one end of a smooth spectrum, revealing the behavior of space and time under conditions far beyond everyday experience. This makes them valuable not because they are exotic, but because they clarify principles that apply universally. For now, let this understanding rest. Gravity, before black holes, is already shaping space and time in quiet ways. These effects are small, steady, and continuous, forming the backdrop for everything that follows. With this baseline established, we can move gently toward the idea that space and time are not separate at all but parts of a single structure that responds as a whole to mass and energy. To understand how black holes bend space and time, it becomes useful to let go of the idea that space and time are separate things. In everyday language, space feels like the area around us, and time feels like the steady progression of moments. We measure distances with rulers and durations with clocks, and the two seem independent. Yet in the physical description that applies at large scales and high precision, space and time are woven together into a single structure. Changes in one are inseparable from changes in the other. This combined structure is often called space-time. The word itself is less important than the idea behind it. Events in the universe are defined not only by where they happen, but also by when they happen. A location without a time, or a time without a location, has no physical meaning. Motion then becomes a path through this four-dimensional structure, tracing both position and duration together. Even when objects appear stationary in space, they are still moving steadily through time. In regions where gravity is weak, space-time is nearly flat. Distances behave as expected, and clocks tick at almost identical rates regardless of location. This flatness is an approximation, but a very good one for most purposes. It allows us to separate space and time in practice, even if they are not truly independent. This approximation begins to break down as mass and energy become more concentrated. When mass is present, space-time responds. Distances between points change slightly, and the rate at which time passes becomes position-dependent. These changes are not imposed from the outside, they arise naturally from the presence of energy and mass. The equations that describe this response do not treat space as a container and time as a background. Instead, they describe how the geometry of space-time adjusts itself continuously. One way to notice this adjustment is through motion that appears curved. An object moving freely, without any forces acting on it, follows the straightest possible path through space-time. In flat space-time, this corresponds to motion at constant speed in a straight line. In curved space-time, that same principle leads to paths that appear curved when viewed in space alone. The object is not being deflected by a force, it is simply following the geometry available to it. Light follows these same rules. Even though light has no mass, it still travels along the straightest paths through space-time. Near massive objects, those paths curve, causing light to bend. This bending is a direct expression of space-time geometry, not an interaction between light and a force. Observations of this effect provide some of the clearest evidence that space and time form a unified structure influenced by mass. Time's behaviour is equally tied to this geometry. A clock measures the length of its own path through space-time. When space-time is curved, the lengths of different paths differ, even if they begin and end at the same events. This is why clocks at different locations or in different motions can accumulate different amounts of time. Near a massive object, the geometry stretches the time component of space-time, leading to slower ticking relative to distant clocks. These effects are small near Earth, but they are not negligible. Satellite navigation systems, for example, must account for both motion-related and gravity-related time differences to function correctly. This practical application underscores that space-time curvature is not an abstract concept, but a measurable feature of the world. It operates quietly, shaping both motion and timekeeping in ways that can be tested and confirmed. As mass increases and becomes more concentrated, space-time curvature grows stronger. There is no special threshold at which space and time suddenly merge or separate. They are always part of the same structure. What changes is the degree to which that structure is curved. Near black holes, this curvature becomes extreme, but it remains governed by the same principles that apply in gentler environments. This unified view also clarifies why black holes affect time as well as space. It would be incomplete to describe their influence as purely spatial. Any change in the geometry of space-time necessarily involves both components. distances shorten or lengthen, and time intervals slow or speed relative to one another. These effects are inseparable, even if they are discussed separately for clarity. Holding this idea gently allows the topic to remain grounded. There is no need to imagine space tearing or time breaking. Instead, picture a smooth, continuous structure that becomes more curved as mass and energy concentrate. This curvature guides motion and shapes the passage of time without introducing discontinuities or sudden changes. With this framework in place, black holes can be approached as regions where space-time curvature has become very strong, rather than as objects exerting extraordinary forces. The next step is to look more closely at how mass produces curvature, and why increasing mass leads naturally to deeper bending of the space-time structure. For now, let the idea of space and time as one connected fabric settle, steady and unhurried, forming the basis for everything that follows. With space and time understood as a single connected structure, it becomes possible to describe how mass changes that structure in a precise and gradual way. Mass does not act by sending signals outward or by exerting a pull across empty space. Instead, it alters the geometry of space-time in its immediate surroundings. The greater the mass, and the more concentrated it is, the stronger this alteration becomes. This relationship is steady and proportional, not sudden or erratic. In regions with small amounts of mass, the curvature of space-time is slight. Distances behave almost as they would in empty space, and time passes at nearly the same rate everywhere. This is why, for most daily activities, classical physics works so well. The curvature is present, but it is gentle enough to be ignored without noticeable error. Only when measurements become very precise does the underlying geometry begin to matter. As mass increases, space-time curvature deepens. This does not happen by adding a new effect on top of existing space. Instead, the structure itself changes shape. The shortest paths through space-time, which determine how objects move, bend more noticeably. Orbits become tighter, light paths curve more strongly, and time differences between locations become easier to measure. These changes are all expressions of the same underlying adjustment. Density plays a central role in this process. A large mass spread out over a wide region produces less curvature than the same mass compressed into a smaller volume. This is why compact objects exert stronger gravitational effects than diffuse ones. The geometry of space-time responds not only to how much mass exists, but how closely that mass is packed together. Compression intensifies curvature without altering the fundamental rules. This principle explains why stars, planets, and black holes differ in their gravitational influence, even when their masses are compared. A star that has expanded into a large volume produces a gentler curvature than a smaller, denser object of similar mass. As matter is compressed, the surrounding space-time adjusts more sharply, guiding motion inward more strongly and slowing time more noticeably near the object. Importantly, this adjustment remains smooth. There is no point at which space-time suddenly becomes distorted. Each increase in density produces a corresponding increase in curvature, following continuous equations. This continuity allows physicists to model gravitational systems across a wide range of scales using the same mathematical framework, from planets to stars to black holes. The idea of curvature can be approached observationally rather than abstractly. When objects orbit, when light bends, or when clocks tick at different rates, these are not separate phenomena. They are different ways of measuring the same geometric change. Curvature reveals itself through motion and timekeeping, offering multiple consistent perspectives on the same underlying structure. Near very massive and dense objects, these effects accumulate. Paths that would be straight in flatter regions become strongly curved. Time intervals that would match elsewhere begin to diverge significantly. Yet even here, the behaviour remains lawful and predictable. The geometry may be steep, but it is not chaotic. This perspective also removes the need to imagine gravity as an added influence. There is no invisible agent pulling objects inward. Objects simply move according to the shape of space-time around them. When that shape becomes steeply curved, motion naturally converges toward the region of greatest curvature. This is true for matter and for light alike. As this idea settles, black holes begin to appear less mysterious. They represent situations where mass has become so concentrated that space-time curvature grows very strong in a localized region. Nothing about the underlying process is unique to them. They are an extension of the same relationship between mass, density, and geometry that operates everywhere else. In the next part, we'll follow this process more concretely, looking at how massive stars evolve and how gradual compression leads, in some cases, to the formation of black holes. For now, allow the idea of curvature driven by mass and density to rest, steady and continuous, forming a clear link between everyday gravity and its most extreme expressions. Before a black hole exists, there is usually a long period of stability. Massive stars spend most of their lives in a balanced state, with inward gravitational compression matched by outward pressure from energy produced in their cores. This balance is not static, but it is steady. Over millions of years, energy released by nuclear reactions supports the star against collapse, maintaining a roughly constant size and shape. During this time, space-time curvature around the star is strong enough to hold planets and nearby material in orbit, but not extreme. As the star consumes its nuclear fuel, this balance begins to change. The processes that generate outward pressure slow down. Gravity, which has always been present, gradually becomes dominant. The star's core begins to compress, increasing in density. This compression does not immediately create a black hole. Instead, it initiates a sequence of adjustments in structure and energy flow, each step governed by well-understood physical principles. During this phase, the star may shed outer layers or undergo internal rearrangements. These changes redistribute mass, sometimes reducing the overall gravitational influence at a distance even as the core becomes denser. The space-time curvature near the center grows stronger, while the outer regions respond more gently. Throughout this process, space and time adjust continuously, without sharp transitions. For stars of sufficient mass, compression continues beyond the point where ordinary forms of pressure can halt it. The core becomes extremely dense, and the curvature of space-time in its immediate vicinity increases accordingly. This increase affects how nearby matter moves and how time passes relative to distant regions, yet even here the process remains gradual. There is no single moment when the star turns into a black hole in a dramatic sense. From an external perspective, the star's collapse appears to slow as it approaches a critical compactness. Signals emitted from near the core take longer to reach distant observers, and their timing becomes increasingly stretched. This stretching reflects changes in space-time geometry, not a failure of physical laws. The collapse proceeds according to the same rules that applied earlier, now operating in a more curved environment. Eventually, the star's mass becomes confined within a region small enough that the curvature prevents light from escaping outward paths. This condition defines what is later described as a black hole. Importantly, this definition is based on space-time behavior, not on the material properties of the star itself. The formation of a black hole is marked by how geometry shapes motion, rather than by a visible surface or boundary. Throughout this evolution, the star does not introduce new kinds of matter or exotic forces. The same constituents that made up the star continue to exist, now arranged more compactly. Space-time responds to this arrangement by curving more steeply, guiding paths inward and slowing time near the dense core. The continuity of this response is a key feature of the scientific description. This process also highlights why black holes are often described in terms of their mass, spin, and charge. These quantities summarize how the objects shape space-time at a distance. The details of the collapsing star's internal structure become less relevant externally, not because they vanish, but because their effects on space-time outside are fully captured by a small set of parameters. As the star completes its transition into a black hole, the surrounding space-time settles into a stable configuration. Orbits form, light paths adjust, and time differences become consistent. The black hole does not continue changing rapidly. It becomes a long-lived feature of its environment. In this sense, black holes are not moments of ongoing collapse, but enduring structures in space-time. For now, it is enough to see black hole formation as an extension of stellar evolution, governed by the same gradual principles that apply elsewhere. Mass becomes concentrated, density increases, and space-time curvature deepens. In the next section, we will look more closely at density itself, and why compression plays such a central role in bending space and time. Density is often described simply as how much matter is packed into a given volume, but in the context of black holes, it becomes a central factor in shaping space and time. Two objects can have the same total mass and yet influence their surroundings very differently, depending on how that mass is distributed. When matter is spread out, space-time responds gently. When matter is compressed, the response becomes stronger, even if the total mass remains unchanged. In ordinary stars, matter occupies a relatively large region. The distances between particles, though small by everyday standards, are sufficient to limit how strongly space-time curves near any one point. Gravity is present, but its geometric effects are distributed across the star's volume. Time near the surface of a star flows slightly more slowly than far away, and paths through space curve modestly, but these changes remain subtle. As compression increases, the situation changes. When matter is forced into a smaller region, the curvature of space-time becomes steeper near that region. This steepness affects everything that passes nearby. Paths that once allowed escape now bend inward. Time intervals stretch more noticeably relative to distant observers. These changes are not the result of added forces, but of geometry becoming more sharply defined. This relationship between density and curvature explains why size alone is not a reliable indicator of gravitational influence. A very large but diffuse cloud of gas may exert less space-time curvature near its centre than a much smaller, denser object. What matters most is how tightly mass is concentrated. Compression intensifies curvature in a localized way, shaping motion and time most strongly near the dense region. In the progression toward a black hole, density increases continuously. Each stage of compression brings a corresponding increase in curvature. There is no abrupt shift where space-time suddenly behaves differently. Instead, familiar effects grow stronger. Orbits become more tightly bound. Light paths bend more sharply. Time differences between nearby and distant regions become more pronounced. These are quantitative changes, not qualitative ones. It is also important to note that density does not need to be infinite for a black hole to form. The defining feature of a black hole is not infinite density, but the confinement of mass within a region where space-time curvature prevents outward paths for light. This condition can be met before any singular behavior is reached in the mathematical description. The role of density is to bring the system to that point by steadily increasing curvature. From a physical perspective, compression faces resistance. Various forms of pressure arise as matter is squeezed closer together. In less massive stars, these pressures halt collapse at earlier stages, forming dense but stable objects. In more massive stars, gravity overwhelms these resistances, allowing compression to continue. Throughout this process, space-time responds faithfully to the changing distribution of mass. The effects of high density are most noticeable close to the compressed region. Farther away, space-time curvature decreases with distance, and the influence of the dense core becomes weaker. This gradual fall-off ensures that even extreme objects like black holes fit smoothly into their larger cosmic environments. Their presence does not disrupt distant regions abruptly. It alters space-time in a controlled and predictable way. Density also shapes how matter behaves near a black hole once it has formed. Material approaching the dense region follows paths determined by the steep curvature, often settling into rotating structures before moving closer. Time experienced by this material differs increasingly from that measured far away, reflecting the local geometry rather than any internal change in the material itself. As this idea settles, it becomes clear why compression is such a powerful factor in bending space and time. By concentrating mass, compression deepens curvature without introducing new principles. Black holes, in this sense, are not defined by exotic substances or unusual forces, but by the extreme density achieved through familiar physical processes. In the next part, we will observe how one of the most reliable messengers in physics, light, responds to this curvature near black holes. For now, allow the role of density to rest in view, steady and continuous, linking the gradual compression of matter to the deep bending of space-time. Light offers a particularly clear way to observe how space and time bend near a black hole, because its behaviour depends entirely on the geometry through which it travels. Light does not slow down or speed up in response to forces in the usual sense. Instead, it always moves at the same speed locally, following the straightest possible paths available within space-time. When space-time is curved, those paths curve with it. This makes light an especially sensitive indicator of geometric change. Far from any massive object, space-time is nearly flat, and light travels along paths that appear straight. As light approaches a region of increasing mass density, those paths begin to curve gently. Near stars, this curvature is small but measurable. Near much denser objects, the curvature becomes more pronounced. The light is not being pulled or deflected by a force. It is responding to the shape of space-time itself. Near a black hole, this curvature becomes strong enough that light can follow closed or nearly closed paths. There exist regions where light can orbit the black hole, tracing circular or looping trajectories determined entirely by geometry. These paths are unstable, but they illustrate how deeply space-time is bent. The behaviour of light in these regions provides direct evidence of curvature without relying on assumptions about material interactions. As light passes close to a black hole, its direction changes gradually. From a distant observer's perspective, images of background objects appear distorted or multiplied. This effect, known as gravitational lensing, arises because multiple curved paths can connect the same source and observer. Each path represents a different route through curved space-time, arriving with slightly different timing and orientation. Timing is another important aspect of light's behaviour near strong gravity. Signals emitted from regions closer to a black hole take longer to reach distant observers. This delay is not due to a reduced speed of light, but to the geometry through which the light travels. Paths become longer in a space-time sense, and the time component of those paths stretches relative to distant clocks. As curvature increases, there comes a point where all outward-directed light paths bend back inward. This defines the boundary known as the event horizon. At this boundary, the geometry of space-time is such that no path leads outward to distant regions. Light emitted at or within this boundary remains confined, not because it is blocked or absorbed, but because the structure of space-time offers no outward route. It is important to note that this confinement applies only from the perspective of distant observers. Locally, light near the event horizon behaves normally. It moves at the same speed and follows the same local rules as anywhere else. The difference lies in how those local paths connect to the larger space-time. The horizon marks a global property of geometry, not a local physical barrier. Observations of light near black holes have become increasingly precise. By studying the shapes of light rings, shadows, and lensing patterns, astronomers can infer the geometry of space-time around these objects. These measurements confirm predictions based on space-time curvature without requiring direct access to the regions near the horizon. Light also carries information about time distortion. Signals emitted from near a black hole appear increasingly stretched in time to distant observers. Each successive wave arrives slightly later than expected, reflecting the deepening curvature near the source. This stretching is gradual and continuous, increasing smoothly as the source approaches the horizon. Through light, the bending of space and time becomes visible. Paths curve, images distort, and timing shifts, all in ways that align with a geometric description of gravity. There is no need to imagine extreme forces acting on light itself. Its behaviour follows directly from the structure through which it moves. As we let this observation settle, light stands as a calm witness to space-time curvature. It traces the shape of geometry without resistance or alteration. In the next section, we will focus more directly on time itself, exploring how strong curvature near black holes affects the passage of time in a gradual and predictable way. The event horizon is often spoken of as if it were a surface or a boundary in space, something solid or sharply defined. In calmer scientific terms, it is better understood as a boundary in space-time behaviour. It marks the region where the geometry has curved enough that all possible future paths lead inward rather than outward. This definition does not rely on material properties or visible structure. It depends entirely on how space and time are arranged. From far away, the event horizon appears as a clear dividing line. Signals from just outside it can still reach distant observers, while signals from just inside cannot. This difference arises smoothly, without a physical edge. There is no wall or membrane at the horizon, and nothing locally unusual happens at that location. The laws of physics operate there just as they do elsewhere, following the same equations and principles. For an object approaching the horizon, local conditions remain ordinary. Measurements of distance, time, and motion behave as expected in the immediate surroundings. Light travels normally, clocks tick steadily, and physical processes proceed without disruption. The horizon does not announce itself through sudden forces or changes. Its significance lies in how local paths connect to the wider space-time, not in any immediate sensation. The idea of a boundary becomes clearer when thinking in terms of possible futures. Outside the horizon, there exist paths that lead away from the black hole and toward distant regions. Inside the horizon, all future-directed paths move deeper inward. This is not a statement about speed or effort. It is a statement about geometry. The structure of space-time simply does not provide routes that lead outward once the horizon is crossed. Time plays a crucial role in this description. Near the horizon, the distinction between directions in space and directions in time becomes less intuitive. What appears as a spatial direction from far away can take on time-like characteristics near the horizon. This shift is gradual and smooth, reflecting changes in the underlying geometry rather than a sudden transformation. From the perspective of distant observers, objects falling toward the horizon appear to slow down. Signals from the object arrive increasingly stretched in time, each one taking longer than the last. The object never seems to cross the horizon within any finite external time. This appearance is not a physical freezing, but a result of how time is shaped by strong curvature near the horizon. Locally, however, the falling object experiences no such delay. Its own clock advances normally, and it crosses the horizon without encountering anything distinctive. This difference in perspective highlights how time itself is affected by space-time geometry. There is no single, universal timeline that applies equally everywhere. Each path through space-time carries its own measure of time. The event horizon, then, is not a dramatic threshold. It is a quiet feature of geometry, defined by the arrangement of possible paths. Its importance comes from its global role in space-time, not from any local physical marker. Understanding it in this way removes much of the mystery that often surrounds it. This boundary also emphasizes continuity. Space-time does not break or tear at the horizon. The geometry remains smooth, and physical laws remain consistent. The horizon marks a change in connectivity, not a disruption in structure. Everything that happens there follows directly from the same principles that govern weaker gravitational fields. As this idea settles, the event horizon can be seen as a natural consequence of strong curvature rather than an exotic addition. It emerges when mass becomes compact enough to reshape spacetime paths in a particular way. In the next part, we will focus more closely on how time itself changes near strong gravity, exploring the gradual slowing of time as curvature deepens. Time near a black hole does not behave differently because clocks malfunction or processes slow internally. The change in time arises from the geometry of spacetime itself. Each clock measures the length of its own path through spacetime, and when spacetime is curved, those path lengths differ depending on location and motion. Near strong gravity, the time component of spacetime is shaped in a way that causes clocks closer to the mass to accumulate less time compared to clocks farther away. This effect appears gradually. Far from a black hole, time flows almost uniformly. As one moves closer, the difference becomes measurable. A clock positioned nearer to the mass ticks more slowly relative to a distant reference clock, even though locally it feels no change. The clock's mechanisms operate normally. The slowing is not something the clock experiences, it is something revealed only through comparison. The reason for this lies in how spacetime allocates intervals. Near a massive object, more of the spacetime structure is devoted to the time dimension in a way that stretches intervals when viewed from afar. This stretching increases smoothly as curvature deepens. There is no single point where time suddenly slows. Instead, the rate of time change varies continuously with position. For observers far from a black hole, this leads to a distinctive pattern. Signals emitted from closer regions arrive increasingly spread out. Each successive signal takes longer to reach the observer than the previous one. This does not indicate that the emitting process has slowed in its own frame. It reflects the growing difference between the local flow of time near the black hole and the flow of time far away. Near the event horizon, this effect becomes extreme. From a distant viewpoint, time near the horizon appears to slow without bound. Processes seem to stretch indefinitely, never quite completing. Yet this is a feature of the distant perspective. Locally, time remains steady and finite. The divergence arises because spacetime near the horizon connects to distant regions in an increasingly indirect way. This difference between local and distant measurements highlights an important aspect of time in curved spacetime. Time is not a single universal quantity that all observers share equally. Each observer carries their own measure of time along their path. Comparisons between different paths reveal differences that become significant in strong gravity. The gradual nature of time slowing also reinforces continuity. There is no break in time, no pause, and no reversal. The progression of time along any given path remains smooth. What changes is the relationship between different paths. Near a black hole, those relationships become more uneven, reflecting the underlying curvature. This behavior of time has practical consequences beyond black holes. Similar though much smaller effects occur near planets and stars. Clocks at different heights on Earth tick at slightly different rates. Satellites must account for these differences to maintain accurate positioning. The extreme case near a black hole follows the same rules, applied more strongly. By viewing time slowing as a geometric effect rather than a mechanical one, the phenomenon becomes easier to place within a broader context. It is not a special property of black holes alone, but a natural outcome of how spacetime responds to mass. Black holes simply provide conditions where the effect becomes unmistakable. As this idea settles, time near a black hole can be understood as part of a smooth gradient. Far away, differences are negligible. Closer in, they grow steadily. Near the horizon, they dominate comparisons with distant regions. Throughout, time itself remains continuous along each path. In the next part, we will return briefly to motion, looking at how objects can move and orbit near black holes in stable, predictable ways. even in regions where space and time are strongly curved. Even in the presence of strong space-time curvature, motion near a black hole remains structured and predictable. It is easy to imagine black holes as regions where order breaks down, but the opposite is often true. The geometry around a black hole defines clear paths that objects can follow, including stable orbits that persist for long periods. These orbits arise from the balance between motion through space-time and the curvature produced by the black hole's mass. Far from the black hole, motion resembles the familiar orbital patterns seen around stars and planets. Objects move along paths that are only slightly curved, and time differences between locations remain small. As one moves closer, curvature increases, and orbital paths adjust accordingly. Orbits become tighter and require greater speed to maintain stability, but they remain well-defined and calculable. There exists a range of distances where stable circular orbits are possible. Within this range, an object can circle the black hole indefinitely without falling inward or escaping outward, provided no additional disturbances occur. These orbits are determined entirely by space-time geometry. The object does not resist gravity or struggle against a pull. It follows the natural paths available in the curved structure around it. Closer still, the nature of orbits changes. Stable circular paths give way to unstable ones, where small disturbances can send an object inward or outward. This transition is smooth and predictable. It marks a change in the shape of available paths rather than a sudden loss of order. Even here, motion follows precise rules derived from the geometry of space-time. Light too can occupy special orbital paths near a black hole. These paths lie at specific distances where curvature allows light to circle the object. Although these orbits are unstable, their existence demonstrates how deeply space-time is shaped. They also influence how black holes appear to distant observers, contributing to the characteristic rings and shadows seen in observations. The predictability of motion near black holes is one reason they can be studied so effectively. By observing how matter and light move, scientists can infer the underlying space-time geometry. Patterns in orbital motion reveal mass, spin, and other properties, all without requiring direct interaction with the black hole itself. Time continues to play a role in these motions. Orbits closer to the black hole experience stronger time differences relative to distant regions. A clock moving along a tight orbit near the black hole accumulates less time than one farther away. Yet along the orbit itself, motion proceeds smoothly, without interruption. The object's own experience remains continuous. These structured motions also allow black holes to integrate into larger systems. In galactic centers, stars orbit massive black holes over long periods, tracing predictable paths. Gas clouds form rotating disks, gradually settling into stable configurations. The black hole acts not as a disruptive force, but as an organizing center defined by geometry. This stability underscores the idea that black holes are not chaotic sinks. They are regions where space-time curvature is strong but orderly. The same equations that describe gentle orbits around planets also describe these more extreme environments, differing only in scale. As we allow this view to settle, motion near a black hole appears less dramatic and more continuous with the rest of the universe. Objects move, orbit, and evolve according to geometry, not struggle or collapse by default. In the next section, we will move inward conceptually, considering what can be said about regions beyond the event horizon while remaining grounded in established physics. Beyond the event horizon, descriptions must remain careful and restrained, because the region cannot be observed directly from the outside. What can be said comes from extending well-tested physical laws into a domain where their consequences become more severe. Within these limits, physics still provides a structured account of how space-time behaves, even if some details remain beyond verification. Crossing the horizon does not involve encountering a surface or a sudden change in local conditions. The geometry of space-time remains smooth at that location. For an object moving inward, distances and times in the immediate surroundings behave normally. The defining change is not local sensation, but global structure. Once inside, all future directed paths lead further inward, toward regions of stronger curvature. This inward direction is not a spatial choice in the usual sense. Inside the horizon, what was once a radial spatial direction effectively becomes time-like. Moving inward is no longer optional, just as moving forward in time is not optional outside the black hole. This shift reflects the way space-time geometry has been reshaped by extreme mass concentration. It does not require new forces or interactions. Within this framework, physics can still describe motion, time passage, and causal relationships. Objects follow paths determined by geometry, and clocks continue to measure their own proper time. The progression remains continuous. There is no instant of disintegration or loss of physical law at the horizon itself. The same equations that apply outside can be written inside, though their implications change. As curvature increases further inward, tidal effects become stronger. Differences in space-time geometry across small distances grow, influencing how extended objects move. These effects depend on the size and mass of the black hole. In very large black holes, curvature near the horizon can be relatively gentle, with stronger effects appearing only much deeper inside. This variation again reflects continuity rather than abrupt change. From the outside perspective, information about events inside the horizon cannot be retrieved. This limitation is geometric, not mechanical. Paths that carry signals outward simply do not exist. Inside, however, local processes continue according to their own timelines. This separation of perspectives highlights how space-time geometry governs what can and cannot be connected. It is important to avoid imagining the interior as a region where physics fails completely. While current theories may be incomplete in describing the deepest regions, especially near the central extremes, large portions of the interior can be treated consistently. The uncertainty lies not in the existence of structure, but in our ability to test descriptions of it. Within the horizon, the inward progression of events replaces the outward freedom seen elsewhere. This does not imply chaos or randomness. It reflects a reorientation of space-time directions. Causes still precede effects, and motion still follows defined paths. The ordering of events remains intact along any given trajectory. By keeping the focus on geometry, the interior of a black hole becomes less of a dramatic unknown and more of a continuation of known principles under stronger curvature. The horizon marks a boundary of connection, not a boundary of physical coherence. As this idea settles, it prepares the way to discuss the mathematical concept often associated with black holes, the singularity, in a calm and precise manner. The next part will treat singularities as features of our models, emphasizing what they represent and what they do not, without speculation or emphasis. The word singularity often carries an impression of something physical and absolute, as if it were a location where matter is crushed into an actual point, and all structure disappears. In scientific terms, a singularity is better understood as a feature of our mathematical descriptions, rather than a directly observable object. It marks a region where the equations used to describe space-time predict quantities that grow without bound, indicating the limits of the model rather than a confirmed physical state. In the context of black holes, singularities arise when the inward progression of space-time curvature is extended as far as current equations allow. As mass becomes ever more concentrated in the mathematical description, curvature increases correspondingly. Eventually, the equations indicate that curvature would become infinite at a central point or region. This outcome signals that the model has reached a regime where additional physical effects may need to be considered. It is important to notice what a singularity does and does not represent. It does not describe a place that can be visited or measured directly. It does not imply that matter literally occupies zero volume in a physical sense. Instead, it reflects the breakdown of a particular set of assumptions. The equations remain internally consistent, but they no longer correspond to conditions that can be tested or fully interpreted using the same framework. Within the established description, the singularity lies in the future of all paths inside the horizon. This means that, according to the model, all inward-directed trajectories eventually lead toward this region. The singularity functions as a boundary in time rather than a conventional location in space. This reinforces the idea that inside a black hole, the usual distinction between spatial and temporal directions has changed. Physicists treat this outcome with caution. Rather than assuming that the singularity is a complete and literal description of nature, it is viewed as a sign that additional physics may become relevant at very high densities and curvatures. The presence of a singularity in the equations highlights where current theories reach their limits, not necessarily where physical reality ends. This perspective helps maintain continuity and understanding. Outside and even well inside the horizon, space-time can be described smoothly and reliably. Only when curvature becomes extreme beyond known regimes do uncertainties arise. The singularity does not retroactively disrupt the regions that can be described with confidence. It remains confined to the deepest interior in the theoretical extension. The idea of singularities as model features also clarifies why they do not dominate discussions of observable black hole behavior. All measurable effects of black holes arise from space-time geometry outside the horizon. Orbits, light bending, time distortion, and stability depend on the mass and spin of the black hole, not on the detailed nature of the central extreme region. By keeping singularities in this mathematical context, the topic remains grounded. They are not required to explain how black holes bend space and time in observable ways. They serve as markers of where current descriptions may need refinement, without implying a breakdown of order everywhere else. As this understanding settles, singularities can be held lightly, without emphasis or imagery. They represent boundaries of knowledge rather than dramatic endpoints. In the next section, we will step back outward again, comparing different kinds of black holes and how scale influences space-time curvature while preserving the same underlying structure. When black holes are compared to one another, the most noticeable differences arise from scale rather than from any change in underlying behavior. A black hole formed from a single massive star and a black hole found at the center of a galaxy obey the same physical laws. They bend space and time according to the same principles. What changes is how extended those effects are, and how gradually they appear across distance. Smaller black holes formed from stellar collapse concentrate their mass into a relatively compact region. The curvature of space-time near them increases rapidly as one approaches. Distances change quickly over short scales, and time differences between nearby and distant regions become pronounced within a small area. These black holes create steep gradients in curvature, even though their total mass may be modest by cosmic standards. Larger black holes, especially those found at galactic centers, contain far more mass. Yet because that mass is spread across a much larger region, the curvature near their outer boundaries can be comparatively gentle. The event horizon of a very massive black hole can encompass a region where space-time changes slowly from one point to another. An object near such a horizon may not experience extreme local effects immediately, even though the overall structure is deeply curved. This contrast highlights the role of scale in shaping experience. Strong curvature does not always mean sudden or violent change. In larger systems, the same total curvature is distributed over a wider area. Time differences accumulate more gradually, and spatial paths curve gently at first, becoming steeper only deeper inward. The geometry remains smooth and continuous throughout. Despite these differences, the defining features remain consistent. All black holes possess horizons defined by space-time connectivity. all shape the motion of matter and light according to geometry. All produce time differences that increase with proximity. The variation lies not in kind, but in degree. Scale determines how quickly these effects become noticeable, not whether they occur. Observationally, this means that black holes of different sizes can be studied in similar ways. Orbits of stars, motion of gas, and bending of light all reveal the same geometric patterns, adjusted for scale. By comparing these patterns across systems, scientists can confirm that a single framework applies broadly, from the smallest black holes to the largest. This continuity reinforces the idea that black holes are not special cases requiring separate explanations. They are part of a unified description of gravity and space-time. Scale changes the landscape, but the train follows the same rules everywhere. As this idea settles, it becomes easier to view black holes as regular features of the universe rather than exceptions. Their differences reflect size and context, not fundamental departures from known physics. In the next part, we will widen the view further, placing black holes within their larger environments and examining how their influence extends outward into galaxies over long timescales. Black holes do not exist in isolation. They are embedded within larger structures, most often galaxies, where their influence unfolds over long periods of time. In these environments, the bending of space and time produced by a black hole becomes part of a broader gravitational landscape shaped by stars, gas, and dark matter. The black hole contributes to this landscape without dominating it everywhere. At the centres of many galaxies, a massive black hole sits in a region of high stellar density. Stars orbit this central mass in predictable paths, responding to the combined curvature created by all nearby matter. The black hole's contribution becomes most apparent close to the centre, where its mass concentration steepens space-time geometry more strongly than the surrounding stars can. Farther out, its influence blends smoothly into the overall galactic structure. This blending is gradual. There is no sharp boundary where the black hole's effects suddenly begin or end. Instead, space-time curvature transitions continuously from being dominated by the black hole near the centre to being shaped primarily by distributed galactic mass farther away. This continuity allows galaxies to remain stable over billions of years, with black holes acting as long-term structural elements rather than disruptive forces. Gas and dust within galaxies also respond to this geometry. Over time, material can settle into rotating patterns around the central region, guided by space-time curvature and conservation of motion. These structures evolve slowly, adjusting as mass distributions change. The black hole does not pull matter inward indiscriminately. It shapes the paths available, allowing matter to orbit, drift, or gradually move inward depending on conditions. Time differences associated with the black hole's presence are also localized. Near the central region, clocks would tick more slowly relative to distant regions. Farther out, this difference diminishes, becoming negligible on galactic scales. Time across the galaxy remains largely uniform, with only subtle gradients near the centre. This again reflects how curvature weakens smoothly with distance. Over cosmic timescales, black holes and galaxies evolve together. The black hole's mass may increase gradually as it incorporates surrounding material, deepening local curvature. At the same time, the galaxy's structure responds, redistributing mass and adjusting motion. These changes occur slowly, preserving overall stability rather than creating sudden transformation. By viewing black holes within this wider context, their role becomes clearer. They are not isolated distortions of space and time, but integrated features within much larger systems. Their influence is strongest nearby and fades with distance, following the same geometric principles that govern all gravitational interactions. As this perspective settles, attention can widen further, beyond individual galaxies, to the way gravity shapes time and space throughout the universe. In the next part, we will step back from specific objects and consider how the bending of time by gravity appears as a general pattern, present everywhere, not only near black holes. When the view widens beyond individual objects, the bending of time by gravity appears as a general pattern rather than a special case. Everywhere in the universe, time flows at slightly different rates depending on the distribution of mass and energy. These differences are usually small, but they're always present. Black holes represent an extreme end of this pattern, not a separate category. The same relationship between mass, curvature, and time operates on every scale. In regions with little mass, space-time is close to flat, and time differences between locations are minimal. As mass becomes more concentrated, the local flow of time slows relative to distant regions. This slowing does not require unusual conditions. It follows directly from the geometry of space-time. The presence of any mass alters time's progression slightly, even if the effect is too small to notice without careful measurement. Across the universe, this leads to a quiet variation in time. Clocks near stars tick more slowly than clocks far from them. Clocks in dense regions of galaxies differ subtly from those in sparse intergalactic space. These differences accumulate gradually, shaping how long processes take when compared across large distances. Time remains continuous everywhere, but it is not uniform in a global sense. Black holes make this pattern easier to recognize because their mass is so concentrated. Near them, time differences become large enough to dominate comparisons with distant regions. What appears as an extreme phenomenon is, in fact, a magnified version of a universal behavior. The same equations that describe time near a black hole also describe time near a planet, differing only in magnitude. This perspective removes the need to isolate black holes as special time-altering entities. They do not introduce new rules for time. They reveal how existing rules operate when curvature becomes strong. Time does not slow because something unusual happens at a black hole. It slows because space-time geometry responds consistently to mass and energy. Over cosmic distances, these variations in time contribute to the overall structure of the universe. Processes unfold at slightly different rates in different environments, yet remain coordinated through space-time connections. There is no single cosmic clock governing everything equally. Instead, time is local, carried along paths shaped by gravity. As this idea settles, time can be understood as adaptable rather than rigid. It flows steadily along each path, while comparisons between paths reveal differences shaped by curvature. Black holes simply provide clear reference points for seeing this adaptability in action. In the next part, attention will shift from time to scale more broadly, considering how black holes fit into the continuous range of structures in the universe, from the smallest masses to the largest formations, without breaking the underlying order. Scale provides another calm lens through which black holes can be understood. When viewed across the full range of cosmic structures, black holes occupy a place within a continuous hierarchy rather than standing apart from it. From small concentrations of mass to vast assemblies of galaxies, the same principles govern how space and time respond. What changes is the extent over which these responses are felt. At the smallest scales, individual particles contribute negligibly to space-time curvature. Their influence is real, but far below what can be detected. As mass aggregates into larger structures, planets, stars, and stellar systems, the curvature becomes measurable. Paths through space bend slightly, and time differences appear when comparisons are made with sufficient precision. Each increase in scale brings a corresponding increase in observable effect. Black holes emerge naturally at one end of this spectrum, where mass has become both large and compact. They do not interrupt the sequence, they complete it. Their strong curvature represents the accumulation of effects already present in milder forms elsewhere. In this sense, black holes are not exceptional objects, but limiting cases of a continuous process. This continuity allows scientists to move between scales without changing conceptual tools. The equations that describe a satellite orbiting Earth also describe stars orbiting a black hole, once scale is accounted for. The same geometric language applies, adjusted smoothly to fit different magnitudes. There is no need to introduce special rules when passing from one scale to another. Scale also shapes how black holes are experienced observationally. From very far away, a black hole's influence may be indistinguishable from that of any other massive object of similar mass. Only when distances shrink does curvature become more pronounced. This gradual revelation reinforces the idea that black holes are embedded within the same space-time fabric as everything else. Across cosmic history, scale evolves, matter clumps, structures grow, and space-time curvature adjusts in response. Black holes form as part of this ongoing process, shaped by the same tendencies toward aggregation and stability seen elsewhere. Their presence reflects the universe's capacity to organize mass across vast ranges, not a deviation from it. By keeping scale in mind, the bending of space and time near black holes becomes easier to situate. It is neither isolated nor singular. It is one expression of a broader pattern that extends from the smallest measurable effects to the most pronounced. The universe presents no sharp boundaries between these regimes, only smooth transitions. As this understanding settles, attention can return gently toward more familiar regions of space. In the next section, we will move back outward, re-establishing the connection between extreme curvature and the space-time conditions experienced in ordinary environments, allowing the contrast to soften rather than sharpen. When attention returns from extreme curvature to more familiar regions of space, the continuity of space-time becomes clearer. The conditions near black holes are not separate from ordinary environments, they are connected through gradual change. The same space-time that bends strongly near dense mass becomes nearly flat as mass thins and distance increases. There is no dividing line between these regimes, only a steady easing of curvature. In regions like our solar system, space-time is shaped primarily by the sun and planets. The bending of space is gentle, and time differences are small. Orbits remain stable over long periods, and clocks tick at rates so similar that differences are noticeable only with careful measurement. These conditions feel familiar because they align closely with human-scale experience. Yet the same geometric principles apply here as near a black hole. Objects move along paths defined by curvature, even if that curvature is slight. Time flows along each path according to the local structure of space-time. The difference lies only in degree. What appears dramatic near a black hole is simply magnified geometry, not a change in kind. This continuity allows black holes to serve as reference points rather than anomalies. By understanding how space-time behaves under extreme curvature, physicists can better interpret subtle effects elsewhere. Measurements made near Earth or within the solar system gain context when placed along this continuous scale of curvature. It also reinforces a calm perspective on gravitational phenomena. Space and time are always responding to mass and energy, shaping motion and duration quietly. Most of the time, these responses are small enough to fade into the background of experience. Only under extreme conditions do they become unmistakable. As this view settles, the universe appears less divided between ordinary and extraordinary regions. Instead, it presents a smooth landscape of space-time, gently varying from place to place. Black holes occupy one region of this landscape, not its edge. In the next section, the perspective will widen once more, touching briefly on long-term patterns and evolution, without emphasis, allowing the idea of gradual change to extend across time as well as space. Over long periods, the bending of space and time participates in slow patterns of change that unfold across the universe. These patterns do not rely on sudden events or sharp transitions. They emerge from steady interactions between mass, motion, and geometry. Black holes take part in this process without directing it. They respond to the same rules of evolution that shape stars, galaxies, and larger structures. As matter moves and redistributes, space-time adjusts. Regions of higher density deepen curvature, while regions that thin out become closer to flat. This adjustment happens continuously, with no need for coordination or timing. The universe does not move toward a particular state all at once. Instead, local changes accumulate, shaping global structure over immense durations. Black holes change slowly. Their mass can increase as surrounding material follows curved paths inward over long timescales. This growth alters local spacetime geometry in small increments, which then influence nearby motion. The effects spread outward gradually, blending into the larger environment without disruption. Even over billions of years, these changes remain measured and orderly. Time itself participates in this evolution. Because time flows differently in different regions, long-term processes unfold at slightly different rates across the universe. These differences do not create conflict or instability. They simply reflect the local geometry along each path. When processes are compared across large distances or long durations, the variations become part of the broader pattern. This view places black holes within a calm evolutionary context. They are not endpoints or interruptions. They are stable features that persist, interact, and change slowly alongside everything else. Their strong curvature marks regions of concentrated mass, but their presence does not isolate them from the rest of space-time. By allowing evolution to be gradual and distributed, space-time maintains continuity. There is no moment when space or time resets or transforms suddenly. The universe changes through accumulation, not replacement. Black holes exemplify this approach by embodying long-term stability within extreme conditions. As this understanding settles, the focus can soften. The bending of space and time becomes part of an ongoing, unhurried process. Nothing needs to be resolved or concluded. The universe continues shaping itself through gentle, persistent change. In the final sections, attention will return to a quieter frame, allowing the continuity of space-time to feel present and unbroken, preparing the mind to rest within that steady motion. As the focus returns fully to familiar scales, the bending of space and time can be allowed to fade back into the background where it usually resides. In everyday environments, space-time curvature is present but mild. It guides motion quietly, keeping planets in their paths and clocks in near agreement. These effects do not demand attention. They operate steadily, forming the unnoticed structure beneath ordinary experience. The same continuity that connects black holes to galaxies also connects galaxies to rooms, roads, and resting bodies. Space here is close to flat. Time here flows almost uniformly. The differences that exist are real, but small enough to remain hidden unless carefully measured. This does not diminish their significance. It simply reflects how scale shapes perception. Understanding black holes, then, does not pull the mind away from the present. It brings clarity to the fact that the same space-time extends everywhere, changing gradually rather than abruptly. There is no need to imagine distant extremes as separate realms. They belong to the same structure that holds familiar places together. This perspective allows attention to settle. Nothing about space or time needs to be actively interpreted or managed. Their behaviour is already determined by geometry and mass, unfolding without intervention. The universe does not rush toward outcomes. It maintains continuity through steady relationships. As these ideas rest, the distinction between extreme and ordinary softens. Black holes no longer stand as dramatic exceptions, but as quiet confirmations of a broader order. The bending of space and time is always present, always proportional, always continuous. With this calm return to familiar scale, there is nothing left to pursue or resolve. The structure of space-time remains in place, supporting motion and rest alike, whether noticed or not. At the end of this exploration, There is no need to gather conclusions or hold on to specific details. Space and time continue bending and flowing everywhere, guided by mass and motion, without pause or emphasis. Black holes are part of this flow, neither separate nor central, simply regions where the structure becomes more visible. The universe maintains its continuity through gradual change. Curvature increases and decreases, time stretches and relaxes. Motion follows paths shaped long before any observation, and long after attention moves on. Nothing in this process demands urgency or resolution. Resting within this understanding does not require effort. The same space-time that curves near black holes supports quiet moments as well. It carries everything forward gently without interruption. Everything flows. Sleep in that motion.